Hello, this video covers the colours of transition metal complexes, also UV invisible spectroscopy, and transition metals as catalysts. So as we've met before, when we have a transition metal atom or an ion, one that doesn't not complex with any ligands, then those 5 orbitals that are in the 3D subshell are degenerate. Remember, degenerate means that they have the same energy, they are of equal energy. This changes when ligands are bound to the central metal ion. For example, if we look at an octahedral complex, so this has got a central copper ion surrounded by 6 water ligands. Now the 6 water ligands will approach along the X, Y, and Z axes, okay? If you imagine it's an octahedral complex, so that all the bond angles are at 90 degrees. The electrons that are in the d orbitals that lie along those axes will be repelled by the electrons of the approaching ligands. Okay, remember your 5d orbitals. There are 3 of them which lie in between the axes, the dxy, the dxz, and the dyz. And there are 2 orbitals, the dx squared minus y squared and the dz squared, which lie along the x and y axes and the z axis. So the electrons in those orbitals, the ones that lie along the axes, will be repelled by these electrons that are from the approaching ligands. So what happens is the repulsion causes the d orbitals to change energy, the ones that are split. So the ones that are on the axis have a higher energy when they're in a complex, more energy than the ones that lie along the axes. So therefore, when you're in a complex, the d orbitals are no longer degenerate. These 3, the dxy, the dyz, and the dxz, have the same energy, but the dz squared and the dx squared minus y squared have different energy. They have a higher energy, and this is due to the repulsion from the approaching ligand electrons. This is called splitting of the d orbitals. Now the energy difference between the 2 different sets of d orbitals depends on the ability of the ligand to split the d orbitals. So if we have a look here, this is the energy difference delta here. Some ligands can have large d orbital splitting, so the value of delta will be large. You will have a high energy difference between the lower energy d orbitals and the higher energy d orbitals. Some ligands can split it to a smaller extent, so the value of delta will be much smaller. So the energy difference between those different subsets of d orbitals depends on their ligand's ability to split the d orbitals. And in fact, ligands are ranked in something called the spectrochemical series, and then they're ranked in order of how well they split the d orbitals. Ligands that cause a large difference in energy between the subsets of the d orbitals are strong field ligands, so that give you a large value of delta, and the weak field ligands cause a small energy difference. You are not expected to memorize, sorry, that should not say the electrochemical series, that should say spectrochemical series. You are not expected to memorize the spectrochemical series. You are sometimes given parts of it, but you should understand that it exists, and therefore different ligands have different field strengths, okay, and can split the d orbitals to different extents. So for example, iodine, bromine, chlorine have small d orbital splitting, so therefore the value of delta would be lower than, say, for example, if you had a ligand of ammonia or the cyanide ion. There would be a much larger value of delta because they're strong field ligands. Okay, so now we've split the d orbitals. The color is actually due to d transitions, and the name kind of gives away exactly what happens. You get a transition between the lower set of d orbitals to the higher set of d orbitals, and it's electrons that move from the lower to the higher. As we've seen before, whenever you promote an electron from a lower level to a higher level, energy is absorbed. In the case of transition metal complexes, light is absorbed and the electrons are promoted from a lower energy d orbital to a higher energy d orbital. Obviously, there needs to be electrons in the lower d orbitals for this to take place, and there needs to be space in the higher d orbitals for the electron to be promoted to, for this to happen. If the difference in energy, delta, corresponds to light in the visible region of the spectrum, then the complex will be colored. And we can predict the color. Whichever light is absorbed, then the complementary color will be observed. And in your data booklet, there's a color wheel that looks like this, okay? So for example, say for example, your complex is absorbing light of a wavelength in the purple region, then the observed color of the complex will be green. So you just look for the opposite color. If your complex is absorbing light in the yellow region of the visible spectrum, then the color that you will see of the complex will be blue. So whichever color is absorbed, the complementary color is transmitted. Now, different ligands, as we saw from the spectrochemical series, produce different energy differences. So that actually means if you have the same metal ion in the center, if you change the ligand, you can actually change the color. So complexes of the same metal ion with different ligands can have different colors. In the water complex with copper that we saw earlier, the energy gap corresponds to energy of yellow light, and so therefore that complex is blue. We observe the complementary color of the light that is absorbed. The greater the splitting, the more energy that's needed to promote an electron from the lower group of orbitals to the higher ones. Greater energy corresponds to shorter wavelengths. So if you have a higher value of delta, then more energy, light of a higher energy is absorbed, which means it's a shorter wavelength. Okay, so as splitting increases, then the light absorbed will tend to shift away from the red end of the spectrum and towards the orange or the yellow. Now, scandium is a member of the D block. It only has one ion, and that's the Sc3 positive ion. That Sc3 plus ion has no d electrons. If you have no d electrons, then d to d transitions cannot take place, and so therefore scandium-3 complexes are colorless. In zinc forms one ion, the Zn2 plus ion. The 3d level is completely full. Okay, 3d10. So there's no gaps to promote an electron into, and so zinc complexes are also colorless. This is why scandium and zinc are not always considered transition metals, because they don't have a partially filled D subshell. The demonstration here, what we tend to do, I can't do this one at the moment, but I will do it when we can get back into a laboratory situation, is to use a prism to disperse white light into the colors of the visible spectrum. And then we place colored solutions in that beam of light. And you should be able to see that if you put for example, a purple solution, if we put a solution of potassium permanganate in the beam of light, then you will see that the green light from the visible spectrum has been absorbed, so the green light actually disappears. If you put a solution of copper sulfate, which is blue, into the beam of light, then you will see that the yellow wavelengths of light disappear. Okay, now we can use this fact to be able to analyze substances using spectroscopy. So remember, if the absorbed energy is in the visible part of the electromagnetic spectrum, we will get a colored compound. And if we have a colored compound, we can use visible spectroscopy, which is called colorimetry. The absorbed energy, if you have a really large value of delta, so a high energy gap, can actually go into the ultraviolet region of the EM spectrum, in which case the compound will be colorless, and we use UV spectroscopy instead. If we have a strong field ligand, like for example the cyanide ion, then the D to D transitions are more likely to occur in the ultraviolet region. You should know that ultraviolet region is 200 to 400 nanometers. You should know that the visible one is 400 to 700 nanometers. Complexes that contain weak field ligands like water, they're more likely to absorb visible light, and this will make them colored. Remember, the complementary color is seen. Whichever color or which wavelengths of light are absorbed, the complementary color is seen. So a UV and a visible spectrometer measures the intensity of radiation transmitted through a sample and compares it with the intensity of the incident radiation. And the absorbance is directly proportional to the concentration. So what happens is you have a light source, okay, passes through a filter if you're measuring a specific wavelength, through your solution under test, and then it is detected. Okay, so the light, the intensity of the light passing through with no sample there is measured, and then the intensity with the sample there. And the difference between those will give you the absorbance. As the concentration of your substance increases, then the absorbance will increase. So we can use it to actually determine the concentration of a substance. There's a video for you to watch that shows you how UV spectroscopy works. Can you please pause this video now and go and watch the UV visible spectroscopy video? Okay, looking at this question, the absorption spectrum of a titanium complex is shown. State which color would be observed. Okay, so you need to look at this is an absorption spectrum, so we need to look at the wavelengths that are being absorbed and then find the complementary color. So using our color wheel, 550 lies in the green region, and so the color of our complex that's observed would be purple. Okay, use the color wheel to find that. Okay, transition metals as catalysts. So you've met them before, so you've met iron in the Haber process, platinum in the Ostwald process, and it's to do with the fact that it's got either unpaired d electrons or unfilled d orbitals, and this can allow intermediate complexes to form. Therefore, we can have reaction pathways that have a lower activation energy compared to the uncatalyzed reaction. The fact that transition metals can exist with more than one oxidation state is also useful in catalysis. Again, we would have done this experiment had we been in a laboratory. There is a link with this assignment to a YouTube video which shows the exact experiment. So you can watch that and use that to record your observations. So you should pause this video and go and watch that YouTube video just now. Okay, so in the reaction, we've got hydrogen peroxide oxidizing potassium sodium tartrate, which is called Rochelle salts, and carbon dioxide is formed. If you mix them, then you will get a very, very, very slow evolution of carbon dioxide gas. Even heating it doesn't produce much carbon dioxide gas. But if you add cobalt-2 chloride as a catalyst, the reaction starts to froth, indicating it's got a large increase in reaction rate. You're getting lots of carbon dioxide gas given off. And the color of the cobalt chloride turns from pink to green. That green is an activated complex. The color then returns back to pink again as the reaction completes. So this shows that the catalysts take part in the reaction, okay, because of the change to the green. So a change actually happens to the catalyst, but they are regenerated, or they return unchanged when the reaction is complete. What actually happens is you get pink cobalt-2 plus ions, which are present in cobalt-2 chloride. these are oxidized to green cobalt-3 ions. They're complexed by the tartrate ions as well, and then are reduced back to cobalt-2 plus ions. Some terms to do with catalysis that you need to know. Homogeneous catalysts even. Homogeneous catalysts are in the same state as the reactants. Okay, the prefix homo means the same. So homogeneous catalysts are in the same state as the reactants. So in that last example, the cobalt-2 chloride solution was in the same state as the hydrogen peroxide and potassium sodium tartrate. So that was an example of homogeneous catalysis. Homogeneous catalysis is a result of the fact that you can change the oxidation state of the transition metal and form intermediate complexes. So that's how that works. Heterogeneous catalysts are in a different state to the reactants. So for example, this would be like your iron in your Haber process. It's in a different state to the nitrogen and the hydrogen. In heterogeneous catalysis, you get intermediate complexes formed, but you also get adsorption. Okay, not absorption where it goes into something, but adsorption where it sticks to the surface. Adsorption of the reactive molecules onto active sites. The fact that the transition metals have unpaired d electrons or unfilled d orbitals is thought to allow these activated complexes to form. And because you've got these alternative reaction pathways, these will have lower activation energies, and so the reaction is catalyzed. Adsorption happens in catalytic converters, which change carbon monoxide into carbon dioxide. So the reactant molecules approach the surface. Here are carbon monoxide molecules. Here's the atoms on the catalyst surface. So the reactant molecules adsorb, so kind of stick to the surface, form weak bonds with the surface of the catalyst. Then there's a bond rearrangement. Okay, so the catalyst breaks the bonds between or inside the reactant molecule while still being adsorbed to the catalyst itself, and then reforms other bonds. So in this case, changes carbon monoxide into carbon dioxide, and then the product molecule leaves the surface. You can now do the check test associated with this section and also questions 61 to 69. As always, if you have any questions, please just ask. Thank you.